All right, everybody, welcome back for another lecture video. This is lecture video number 2 for chapter 5 here on ionic bonding. Now, the next thing on the docket here for chapter 5 is a different kind of structure here. All right, it's a different kind of structure here. We've not yet learned about these, but these types of structures are kind of similar to Bohr models in that you're drawing something based on an amount of electrons. The only difference here, guys, is that the electrons we care about don't come from the electron configuration. They come from the number of valence electrons, right? So that's an important distinction here, right? So whenever we draw a Bohr model, for example, right? Bohr models consist of every single electron at every single principal energy level, right? So for magnesium, right? Magnesium has a configuration, as we know, of 2-8-2, right? And that means that we've got a Bohr model of 1, 2, and 3 principal energy levels with 1, 2, 1, 2, 3, 4, 5, 6, 7, and 8, and then 1, 2 electrons, right, to signify all of the electrons in this Bohr model, right? That's what we got going on here. All right, but again, when it comes to these Lewis dot structures, a little bit different because we're only focusing specifically on the number of valence electrons, right? So on top of that, the starting point for them are also different, right? There's no nucleus involved. All we're doing is starting with the actual, what do you call it, the atomic symbol, right? So we're dealing with an Mg+2 ion. So the atomic symbol for magnesium is, of course, Mg, right? So start with the magnesium atomic symbol. Next up here, to draw the Lewis structure, all we're doing is focusing on the number of valence electrons. Well, how do we get that? Of course, it's going to come from our electron configuration of magnesium, which, as we know, is 2-8-2. And if we remember, our number of valence electrons is always the farthest to the right number, right? The number farthest to the right, in this case, is a 2. So that means magnesium's atom has 2 valence electrons. Now, instead of doing what we did with our Bohr models here, where we did them opposite of each other, right? So if I were to put an electron here, I would only put one across here, then I would go opposites, opposites, opposites. That's not the case this time around, okay? When it comes to putting electrons on a Lewis structure here, a Lewis dot structure, we always want to pair them up into 4 different zones, right? So the 4 different zones are going to be, you can put a maximum of 2 electrons here, a maximum of 2 electrons here on the left-hand side, a maximum of 2 electrons here on the bottom side, and a maximum of 2 electrons here on the right-hand side. So in each of these 1, 2, 3, 4 different zones here, you can only put 2 electrons as a pair in each of those 4 zones. So if we use that idea here, well, we've got 2 electrons to place here. We always want to do our best, guys, to group these electrons together, right, if we have the option to, right? So if we have an even number of electrons, you want to always group them up in terms of where those electrons are going to be grouped, right? If you end up having an odd number, so let's say magnesium had 3 valence electrons specifically, we will put 2 grouped together, and we would just put 1 randomly by itself somewhere else, okay? But if you have the option to group them, you're always going to want to, actually group them. All right, so Mg Lewis structure looks just like this, right? Only caring about valence electrons. Again, Lewis structures are only valence electrons. That's it, right? Now, we want to convert this, though, to be a Lewis structure for an ion, right? So step number 1 asks us to just draw the Lewis dot structure for an atom, which we just did. Now, these next 2 rules here, rule 2 and rule 3, step 2 and step 3 here, should look pretty familiar to what we did in class the other day, talking about doing a Bohr model for an ion, right? Remove or add electrons to be consistent with the charge on the ion, right? If we remember, guys, just like we did the other day, we were looking specifically at the charge of the ion of magnesium, which is a +2. Remembering that the positive symbol here means that we're losing 2 electrons, right? Positive always means losing. And this number here tells us exactly how many we're losing. So we're losing 2 electrons. Again, it's going to be these 2 electrons here. So our new configuration, like we're used to, is going to be 2-8. Okay, 2-8. Now what happens here, guys, is this. The 2 electrons that we have on this Lewis structure for our magnesium atom disappear, okay? Just like they did in our Bohr model for a magnesium ion, right? So that's step 2. We removed 2 electrons to be consistent with the charge on the ion. Okay. Step 3, same thing as last time. Place brackets, right? Brackets are these guys here. Place brackets around the Lewis structure to show the overall charge. So brackets around here, and of course, again, the charge is a +2. So we've now converted this Lewis structure from this here, which is Mg2, or with 2 valence electrons, to become this guy here, Mg +2. Okay, same thing with sulfur. Okay, sulfur, same deal, has a configuration of 2-8-6. Okay, so let's draw a Lewis structure based on the sulfur atom, right? Again, using sulfur, the atomic symbol of S, as the middle portion here. Again, we're using the valence electrons and valence electrons only. Again, Lewis dot structures only care about valence electrons. So we've got 6 electrons to place around this Lewis structure here. I'm going to put a grouping here. Okay, here's 2 right there. Okay, we've got another 2 right here, and another 2 right here. Okay, again, always want to group them together in pairs of 1, 2, 1, 2, 1, 2, right? Always pairs of 2, right? We have an even number this time, so of course we're going to have the total of 3 different pairs here. So this is step number 3, step number 1 in our 3-step process. Draw the Lewis dot structure for the atom. Next up, step 2, remove/add electrons to be consistent with the charge on the ion. As we see here, the charge on our ion is a -2. Again, that negative symbol there tells us we have a negative ion, or our anion, right? Anions end up gaining electrons, right? So the minus symbol means we've gained electrons, and the 2 tells us how many we've gained, which is 2. So we've gained 2 electrons. All right, so we're going to do exactly that, right? That means our configuration is going to change from 2-8-6 to 2-8-8, just like we did the other day with our Bohr model for sulfur. Now, all we do is showcase that by putting 2 more electrons on that side of our Lewis structure here to show that we have fulfilled the octet rule of our 8 valence electrons, right? So we go step 3, brackets on either side with a -2 charge in the upper right. And there we go, okay? Going from Lewis structure of an atom to a Lewis structure for an ion of magnesium and for sulfur, okay? Moving on to our next step here, Lewis structures for ionic compounds, right? Might seem complicated, but it really is just as simple as doing what we just did, but for every piece of our compound here, right? So just simply draw a Lewis structure for each ion and then place them next to each other, okay? Use brackets to indicate charges on each ion, okay? So we're dealing with magnesium oxide, okay? Magnesium oxide is the compound MgO, okay? Magnesium oxide, okay? Which means we should have an Mg Lewis structure and an O Lewis structure, right? So we're going to go ahead and use our reference table to help us out with this one, right? As we know, if we look at magnesium on the periodic table, looking in the upper right-hand corner, magnesium is going to have a +2 in the upper right. Well, if we do the same thing for oxygen, looking at oxygen on the periodic table, looking in the upper right-hand portion of oxygen on the periodic table, tells us we're going to have a -2 charge, right? So let's use those charges to help dictate what happens to our Lewis structures for both magnesium and for oxygen, right? As we know, magnesium is going to end up having 2 electrons in its Lewis structure. Oxygen, if we look at the configuration, oxygen has a configuration of 2-6. That means that 6 is going to represent our number of valence electrons, which is what we use a Lewis structure to help focus on. So we've got 1, 2, 3, 4, 5, 6 total valence electrons in an oxygen ion. In an oxygen atom. Right now, all we do is just utilize our charge, a +2 and -2 for both of these 2 here, to convert them into ions, right? Because you want the magnesium oxide compound, which recognizes that fact that we need ions and not atoms here, right? So converting our magnesium atom into an ion, we remove 2 electrons to be consistent with the +2 charge, put brackets around the left and right-hand side, and a charge to boot of +2. Now with oxygen here, oxygen has a -2 charge. So minus means we're gaining exactly 2 electrons here. So we're going to gain 1 here, and we're going to gain another 1 here. Bracket on the right, bracket on the left, and now, oopsie, now we are simply adding a -2 charge here, okay? Mg +2, and then O -2, right? That right there, this whole thing right here is a magnesium oxide compound, right? It's the Lewis structure for the magnesium oxide compound, right? All right, moving on. Okay, polyatomic ions, right? Visiting these again, revisiting these polyatomic ions, right? Again, they're never going to go away. We're going to see them a bunch this chapter. Not as much next chapter, but we will continue to see them later on in the school year, right? So again, we're touching on them now multiple times to get used to seeing them, but they're not going to go away, right? We're going to see polyatomic ions a lot this school year. A polyatomic ion is an ion composed of more than one element with an overall charge, right? If you look at all these different examples of polyatomic ions present here in table E, we can see that every single one of them are going to have at least two elements present in them, right? Hydronium, H and O. Mercury, right? Hg twice. Ammonium, NH, right? All of them are going to have this rule of having at least two elements or more. Okay. Again, be able to recognize them, not memorize them, recognize them. All right, next thing on the docket here, guys, is to be able to determine the charge on an ion. This thing is relatively easy. It involves a little bit of math, right? So it's not going to be anything too difficult. In the math that we do use is some very, very basic math, very basic algebra, basically using like linear equation type stuff. Very, very simple. Now, we have some common charges to deal with, right? I've used this word common charge, this phrase common charge a couple of times recently, especially last class, okay? Common charge occurs whenever you have an example on the periodic table where, let's say, for example, we've got, let me grab my periodic table here, okay? If we look on the periodic table here, for example, right, someone the other day mentioned sulfur, right? If we look at sulfur in the upper right-hand corner, sulfur has its -2, has a +4 as well, and it also has a +6 below it, okay? But the catch here, guys, is that the charge, right, this is a list of charges, -2, +4, +6. The charge at the very, very top of this list here is the common charge, right? This is your common charge here. So these charges here are always referencing the common charge of that specific element, right? So for example, sulfur is a part of group 16, which means that the common charge of it is always going to be a -2, which just so happens to be the charge we see right here, okay? A little bit of a full circle there, right? So group 1 is going to be +1, group 2 is a +2, group 17 is -1, group 16 -2, group 15 -3, right? These are the knowns, right? What we know for sure is the case, right? If we also run into any polyatomic ions, like we might here, for example, right? If I go back here, right? Polyatomic ions also have their charges listed right in the formula here, right? So if I look at these polyatomic ions, for example, right? Hydronium has a +1, right? If we look over here, carbonate has a -2, right? So the charges are very specific on each of these, right? So especially for our polyatomic ions. And again, these rules for determining charge are only specific to ionic compounds, right? Ionic only, no covalent present here. All right, moving on. Ionic bonds result when two or more ions are attracted to each other. A bond is a result of opposite plus and minus charges attracting each other. And again, referencing the fact that ionic bonds occur between metals and nonmetals, or a polyatomic ion, and really anything else. I know earlier on I specified and said polyatomic ions and metals, but there are some instances, guys, where polyatomic ions are actually bonding to nonmetals, and they are still considered to be ionically bonded. All right, so please make that distinction there, right? If you see a polyatomic ion, it's going to be ionic bonding, plain and simple, right? That's the biggest telltale sign. So if you find and recognize a polyatomic ion, ionic bonding is occurring, right? Regardless if it's bonding to a metal or a nonmetal. Now, ionic compounds, right? Binary compounds are compounds composed of only two atoms. A formula unit is a unit where the chemical formula is indicating the ratio of atoms in an ionic compound, sometimes also referred to as our empirical formula, which we'll talk about later on in the school year. Right, so the formula unit for sodium chloride is NaCl, which tells us that for every one sodium ion you have, you've got one chloride ion. Magnesium chloride, MgCl2, tells us that for every one magnesium ion you have, you've also got two chloride ions, which is distinct by looking at this little 2 present right here, right? This little 2 tells us exactly how many chlorine ions we've got there, right? So the 2 tells us something very specific. Same with potassium, okay? Potassium sulfide is called K2S. That tells us we've got 2 potassium ions for every 1 sulfide ion, okay? We've got this charges and formulas here, this slide here. We'll save this as our, one of our first slides we tackle in class when I see you guys next. But other than that, that's the end of the video.